I'd now like to invite Karl to stand to talk about leather degradability in past and future. Thank you, Karl.
Thank you to the organisers for asking me to speak. I didn't think it was a great idea for the second biggest chatterbox in the industry, part of the biggest chatterbox in the industry, but I'll try and keep us onto time and make sure that we finish by lunch. The SLTC organisation committee had quite a big debate about my title because they were trying to see whether they're grammatically correct its past and future. And that's really what I want to talk about. I want to talk about where we came from is in terms of leather degradability, but also where we're going to take this in the future. Now, there's some of you who have, well, before I get onto that, I'm really glad to see some young people in the room because I think this topic is going to help take our industry forward in many areas, particularly in the marketability, but I'll come on to that a little bit later. Now, I'm going to break my talk into two main parts. I'm going to talk a little bit about the past of leather degradability. I'm going to talk about the future. Now, some of you will be saying, well, why isn't he talking about biodegradability? Because we've heard so much about it in the industry, and surely he should be talking about biodegradability. Well, to start off with, degradability is the big set. And inside the big set of things is the small compartment called biodegradability. Now, some of the older people in the room will be going, oh, we don't want to be talking about this because we make leather that is not biodegradable. Or do we? For as long as we can remember, we've been making leather products globally, thousands of years. Where are all those leathers? Why do we not have huge quantities of Egyptian and Roman artifacts? Where are they? And if they're not biodegradable or degradable in some form, why don't we still have huge quantities of them? Well, the truth is our definition does not have enough nuance. The definition of tanning, being able to take material and render it imputrescible. Over what time span? Everything on the planet is degradable. It just means time. It just takes time to get to that level of degradability. So that's what we're going to be considering today. And before I get onto that, I want to mention one of the most destructive forces on our planet. Everyone's going, oh, he's going to get on the ESG. No, the most destructive force on our planet is microbiology. It does a huge job, much more than humans do in terms of destroying materials on our planet. Of course, many of the things that we use them for are useful, making yogurt, making beer. These are destructive forces that actually produce useful products. In fact, we would be eyeballs deep in trees and plants and animals if it wasn't for the destructive power of these organisms. So they form a very vital part of our ecosystem. And in fact, we have to think about our past. We have to think about the degradation of leather, how it is destroyed, and how these creatures here will actually do that destruction. You might not think as of this process here. This is a picture of some metal rusting. You might not think of this as a degradation process, but of course it is. In fact, it can even be a biocorrosive, biodegradative degradability. You can actually have bacteria involved in helping to break the metal down. So the forces of destruction by microorganisms and of course by our planetary factors essentially mean that most materials will break down at some particular point. Now, Dr. Lama up on the top there, she will recognize something like this. A focus of her research for many years has been acid rot or red rot degradation of materials. And we have to go back to the archives to start to see these destructive forces and start saying, hang on a second, these are actually quite useful in the circular economy or in the end of life technology of materials going forward. So here you can see some vegetable tan material. Of course, the surface is degraded. Those could be biodegradative forces, but most likely they are physical, chemical biodegradation, because that is at the heart of this degradation is what we need to think about. When we're thinking about materials breaking down like leather, we need to think about the chemical, acids, alkalis. We need to think about physical, maceration, breaking, strain, tensile strength, and those kinds of forces. But we also need to think about the biological, the action of enzymes that are actually going to break the material down. And for multiple generations, we've been considering how do we stop our leather from degrading? How do we stop it from breaking? How do we resist biodegradation? How do we tan it? How do we fill it? How do we put coatings onto it so that it doesn't break down? Now, we will need to return back to those archives because in those archives is the key to how we make a better end-of-life material going forward. Why? Why are we even considering this? Why are we considering this? And I'd like to continue Vic's subject earlier about how do we create new and exciting narratives in our industry that we transmit to our customers. Our customers are fascinated by the fact that alternatives are not biodegradable, that have terrible end-of-life and in-life strategies because of their microplastics and terrible end-of-life. Yes, they might be able to do some kind of technosphere recycling, but we know that only 10–15% of plastics are recycled. It's terrible in terms of the actual circularity that these material companies are actually claiming. Whereas here we've got an opportunity, not for all of our leathers, because we have different narratives for other leathers, but for this material, we have a narrative where we can actually say, look, for those people who are concerned about end of life, here is one material that certainly rises amongst our competitors. And so we've got to go back to those archives, and we've got to go and dig out those studies that Dr. Lama's been doing and say, look, can we actually exploit both degradative forces but also biodegradative forces to actually do that? So I mentioned chemical and mechanical, physical degradation. Here's a nice picture of a snow scene. And you can imagine the cold. We just heard about Mount Everest. You can imagine the cold. You can imagine the freeze-thaw cycles that you get in materials. These are massively destructive. And so leather will be the same kind of material. It'll be at low temperature prone to cracking. And so we will do certain things to prevent that. All of that information feeds back into our knowledge of how do we make these materials resistant. We've got light. Light is very destructive. And of course, in this picture, even though we can't see it, we have oxygen, a major degradative force on our planet. In fact, if it wasn't for the oxidation that we get in the oceans, the plastic problem would be even bigger, because the oxidation that we get in the oceans, particularly in that kind of hostile environment, means that the materials break down quite considerably. Here we see wave action in the ocean environment, particularly during stormy seasons. The mechanical and physical breakdown of materials is something that ultimately will break the material into smaller pieces. Now, many of you know that if a material is being broken down smaller, its surface area increases proportionally. And as its surface area increases, the action of all the other degradative forces increases, whether it's biodegradable or by enzymes, physical, chemical, all of those are going to increase significantly. So we need very often the mechanical forces to break things down. At least 3 times per day, you will do a partial degradation on the food that you eat. You will chew it into smaller pieces. You will use chemical processes from the stomach acid. And of course, you will use biological enzyme processes to partially digest and degrade the material down as much as possible. So it's not uncommon for us to see these kinds of natural cycles taking place. So that's a little bit of the history in the past. Let's talk a little bit about how you go about testing this. And I'm going to use compostability as a modern way in which we do these testing. I started working with biodegradability at the university in 2002. We had a PhD student called Sally Jacob, who was fascinated by the biodegradability of leather waste, and in particular wanted to understand how do you get as much biogas as you can. And it was very, very early warning signs that we saw that vegetable tans were not good biodegraders. And our Pete at the back there will be able to confirm with me. It's been something that we've known for 50 years or more, that the actual breakdown of vegetable tans in effluent treatment plants give us a little bit more headache. We have to bombard them with oxygen to actually get them to break down, because the bacteria in those plants are just not able to actually break them down. And so we got this work going in 2002. Sally Jacob got some fantastic graphs showing different levels of biogas generation from different leather wastes. And of course, we started to get some warning signs that things weren't as rosy as we imagined. We thought, of course, hide and skin is biodegradable, but what about the leathers? And of course, the definition for vegetable tan were true. It was rendered imputrescible. Vegetable tan really made it imputrescible. In my laboratory, we've got lots of vegetable tan breakdown pieces, and it almost forms like a clinker, like a stone, a little glassy stone. In fact, I was showing Daryl some of these when he was at my lab the other day. And so these polymers that almost seem to result as the breakdown products of vegetable tan are quite interesting. And I'll come back to vegetable biodegradability in a second. Now, compostability is something that's quite well defined. So if you have this huge set of degradability with biodegradability as a little subset in there, You can also imagine more elements inside that subset would actually covers compostability. And compostability is quite a nice definition because it's very, very, very well defined in the EU. If you want to pass compostability requirements, it is a very specific set of tests that you have to do. And to use the word compostability on your web page as a brand, you need to be very specific about it. Otherwise, our current greenwashing laws are going to eat you alive. Whereas something like biodegradability and degradability is very loosely defined, there's not strong terms about it, and everybody's climbing all over these terms at the moment in the actual environment. So the first element of compostability to satisfy the compostability requirements is metal testing. The material itself, not the compost, the material itself is tested to see what the quantities of metals are. All the usual suspects of metals that you would expect to see on that list are present there. Aluminium is not, because aluminium is so common in soil, they couldn't limit it because there's so much aluminium in soil. It doesn't make any sense. Plants are largely immune to aluminium. And of course, it would be ridiculous for the European Union or anybody to set aluminium because just the soil itself would probably fail their own requirements. And so things like chromium immediately mean that you're not in the ability to market your product as compostable. Unless you can remove the chrome, like we heard earlier, you're largely going to end up with quite a lot of chromium in your compost, and that's going to be absolutely prohibitive. You will not make it past the first hurdle here. This picture shows the typical compost that we have, and you can see some mold growing on the bottom. We often get these white molds. The composts grow, the bacteria and fungi grow. They produce enzymes. Boxes themselves are very hot. So there's quite a high abiotic component. The temperature, particularly for low thermal resistance leathers, really destroys the materials that we have in the box. And of course, the enzymes do their work and disintegrate the material into fragments. So you have to be able to exceed 90% disintegration in the test for you to pass this particular element. So we've had metals, we've had disintegration. Does the material break into fragments? But to get around the problem that many plastics are oxidegradable and break into microplastics, they go further than disintegration in the compostability standard. And they start saying, look, what about the biodegradability? Just a picture of some alternative material. Is Pinatex. But here we have a picture of biodegradability bottles in action. We use 2136. The bottles themselves have a bacterial soup. We place leather powder, shredded down to less than 2 millimeters into the biological soup. And of course, these containers are airtight. We trap the gas coming out of the bottles. We scrub the air going in, so it's CO2 free, and the gas coming out goes into CO2 detectors, and we generate graphs like this. And so we see accumulation of CO2. You can sort of see the one at the top is our collagen control. We use hide powder, and you can see at the bottom we have the leather that we're testing, and the leather itself has a slightly lower biodegradability than the collagen control powder. You'd expect collagen to be very biodegradable, and it always is. Within 90 days, it exceeds 90% biodegradability normally. So we generate these graphs and we get an understanding of just how much a material will break down. Now you might be saying, yeah, but why do you do disintegration and biodegradability? Well, you need to understand that there are multiple steps as you go through the breakdown. We saw the picture of rust. That would be typically what we call biodeterioration, or the darkening of bananas. That will be what we typically would call biodeterioration. And then you start to get this disintegration where the materials start to break into smaller pieces. And then you get the mineralization where the smaller pieces start to get digested by biotic and abiotic forces to the point where they're useful substrate that the microbiology can take into their cells, use in their respiration, and then produce the CO2 that you see here. We're picking this up. This is the CO2 that comes out of the material. Now, how do we know what 100% is? Well, we test your material and we say exactly how much carbon is it. So you're going to hear after lunch from Gustavo, who's going to tell you how to do even more detailed analysis in your carbon. But we will measure the total carbon, and we'll be able to say from the total carbon, theoretically, you're able to produce this much carbon dioxide. So we'll know those particular numbers. So biodegradability, we've had disintegration, and we've had metal. Those are the three criteria to begin with. But it's no good just breaking the material down and then leaving waste and putting that into the ground, polluting the soil. And we've had many cases of this with tannery sludges applied to soils around the world, where later on there are some court cases. where some of the chemistry that is in the soil is, of course, has to be cleaned up and the contamination has to be rectified. So we have to think about the ecotoxicity. And so one thing that we do, particularly some of our partners, they insist on a full ecotox screen, 260 odd chemicals. But one simpler way that you can do it is you can do plant response. And yeah, we've got some bean plants that we'll put the compost that we've made using your material, put them into some pots in a controlled environment room, controlled lighting, controlled watering, controlled feeding, and you grow the plants. And on the left-hand side, you can see the controls, and on the right-hand side, you can see something that the plants haven't liked. They start getting this curling, and you start to see these plants just saying, I'm not happy, not happy. And that's another way in which you can do ecotoxicity. You can even do dose response. So you can dilute the soils with the leather compost that you've got, and you can determine exactly the concentration of compost dosing before you'll start to see negative effects in plants. That's the OECD208 test. And here's another example. You can see on the right-hand side some great plant growth in terms of the blanks. That's what we typically see with our blanks. They love the substrate that we put them in. And then on the very left-hand side, what we call the controls, because at the same time we make your compost, we make a compost that's completely material-free. And you can see, because we've diluted the plant growth substrates, the plants don't particularly like the controls. They sort of look like a grey color. And then the sample in the middle there, it's supplying some of the nutrients that the negative control didn't have. It's got a little bit more of a green color, but you can see the plant height is not as high as the blank on the right-hand side. Now, what do we expect in some of the leathers? Well, vegetable tans don't do well, as I said, in disintegration or biodegradability. But boy, do they do well in this test. Because the material doesn't break down and goes into soil, we get about 200% extra growth compared to the blanks. So if you can imagine the blanks on the right-hand side, you can imagine in the middle, the plant growth will be double the height of the blanks when you put vegetable tans into it. The plants really like this, and we don't understand fully why. It could be that there's an antimicrobial effect, almost like a probiotic effect in the soils. The vegetable tan might be killing some of the harmful bacteria for plants. We also think it's quite closely linked to water moisture. The vegetable tans have a nice high organic moisture content, and they're naturally hygroscopic, so they might hold the water, and the plant sort of work with the veg tans to sort of get that really nice plant height. But this tells us a lot about the ecotoxicity. The final consideration for the compostability requirements in the EU at the moment is a brilliant part of the test. It's overlooked, understated. It's called recognizability. Does the compost that you produce look like this? And here I just went into our lab, picked up some of the compost in one of our inoculant buckets, and you can see just how nice. Granular, dark colored, smells humic, beautiful. And if you produce a compost at the end of the day and it's got little white bits of plastic, or if the compost is green, or if it looks all shredded and doesn't look like compost, no one in the world is going to buy that. No farmer is going to let you put that on their land. So the recognizability test is that final hurdle that you have to get through to be able to say, you've produced a high quality leather compost. Now let's move on and put this onto agricultural land in a circular economy. And that brings me on to the last section here, and you'll be pleased to know there's not many slides here. So these are some of the leathers that we see, and many of the chrome-free materials that we currently have, we see breakdown from about 11 days in compost. So some of them will typically start day 21, 23, and we've had everything. We've had shoes, bags, automotive, upholstery, domestic, chamois is a fantastic biodegrader. You name it. There's not a single article that's currently not in testing for some reason for biodegradability. So many of these chrome frees, we don't particularly entertain customers who say they want to test their chrome leathers. Why? You're going to end up with chrome-containing compost. So your chrome-free compost, and after about 11 days, there's some speculations that we have with the scientists as to why chrome-free materials do so well. It's probably because in industrial composting, the temperature is so high and they are very susceptible. But also, I think that the collagens themselves are not as shielded as some of our more complex tannages. And so you see the enzymes breaking down the collagen into small little pieces quite quickly. And literally in 11 days, you start to see breakdown. Now, I showed you a picture of Pinatex, and you might wonder, why did he include Pinatex? I haven't got anything against Pinatex, but Pinatex is a cellulosic. It's derived from pineapple fiber, like many cottons or cellulosic materials or tensile materials or materials that are cellulose-based that are on the market at the moment. They get put into these kinds of tests and they don't break down in 11 days. In our control boxes for disintegration, we use standard Amazon cardboard, the stuff that comes with our Amazon deliveries, as part of our control, because cardboard breaks down slowly. Within 90 days, you do not get cardboard broken down in compost. And the cellulosics are the same, because they're the same material. So that Pinatex material does eventually break down. It's just very, very slow. So here is a material, leather, that is way faster than most of these other materials. You show the brands and the retailers this kind of performance, and they're immediately interested because it's a story. Vic was talking about stories and narratives that you sell to your customers. This is an interesting story. So this is typically what we see. Eventually, they completely disappear into nothing. And this is linked into closing the loop. It's linked into how do we start with regenerative agriculture, take ourselves through very sustainable manufacturing with all of the ESG components, enter into a very sustainable life because of its long-lived durability, performance expectations. But at some point in that longevity cycle, there may come a point where you want to enter that material into its end-of-life phase. And how can we close the loop back to regenerative agriculture with a process maybe called regenerative end-of-life? Well, of course, you take a leather that will survive during its life, not biodegrade, because like a wooden spoon, the conditions for biodegradation are not met during its life. But at the end of its life, when you put them into a compost, when you put them into an anaerobic digester, the conditions for breakdown are met, the material breaks down into its elements, and we return it back to land safely. In the soil, without any threat with ecotoxicity, we've regenerated the nutrients in the soil. We can grow our plants, we can grow our grasses for our next generation of animals and plants for the loop going forward. This has appealed a lot to particular brands and retailers because they're under pressure to meet recycling targets. And in the European Waste Directive, organic recovery or organic recycling through anaerobic digestion or composting is seen as a recycling method. So many of the shoe companies that we work with want to increase their recycling targets. In the end-of-life vehicle directive, you want to increase your recycling target. And so why don't you use some of the materials that actually have a biodegradable end of life that you can elementally recycle? Colorways, legacy chemistry, as long as it's not ecotoxic, can all be handled. You don't have to worry about mixing, blending colors or trying to match certain materials. Nature will sort it out for you into the elements that it needs for its next particular cycle. Thank you very much.
Thank you very much. Does anyone have any questions for Karl? Or we all got your eyes on the lunch?
Okay, mate.
Finish.
Some do well, some do badly.
You're going to be recycling finished leather.
Yeah.
What happens to the finished leathers?
There are some finishes that do well. As you know, many polyurethanes are prone to hydrolysis. So some of the abiotic components of these tests smash them up. What they smash into, that's a very good question. We don't have data yet on what the byproducts are of complex finishes. In the news this week, we've seen information by scientists that they've found bacteria that can even break down polypropylene, quite a resistant plastic. So we know that the microbiology can do it. What it breaks down into, that's the golden question. So the next stage, and maybe this is a slide that I should include for future talks, is to be able to say, look, part of the ecotoxic screen is what are the microplastics. So what we can do is we can filter some kind of solvent through the soil mixture, and then test the elutants for microplastics as you would normally do. And so that's a key message. There's also techniques that people currently use in cell cytometry, where as the plastics move past an FTIR detector in cell cytometry, you can pick up certain functional groups that you can recognize as plastics. Something that I'm quite interested in is using earthworms as bioconcentration agents in composts, getting them to actually eat the microplastics and then dissecting the earthworms to see what level of microplastic they're picking up, because that must be proportional to the microplastic contamination that you have in the soil. I am convinced that microplastics is a bigger problem than climate change. I think that the scale of microplastic pollution globally, whether it's marine, aquatic, or terrestrial, is off the charts. I really think that we're going to start to see surprises in our soils.
But if you put a piece of finished leather through your, as it were, normal composting process, what do you end up with? A film of finish?
Sometimes it's just the films. So we've got in one of our boxes, the experiment that's been running for 2 years. I took some leather from a car company beginning with T, ending in A, not Toyota, and that's been going for well over 2 years. In fact, I've replaced the compost twice because the compost broke down completely, and so I had to put new compost in. It's gained weight. Whereas in the other boxes, I took some ICLT automotive leather that we made with the MAC students many years ago, and just the finishes are left, the VU finishes. Nitrocelluloses break down very well. Anything cellulosic breaks quite well, depending on how crystalline the celluloses are. Anything protein, even cross-linked proteins, the bacteria smash it to pieces. Some of the newer generation biopolymers, they do quite well. PLA, PHB, they all do particularly well in industrial, not in home composting. And so there's a lot of really interesting finishes. It's the area that we really need development in support. Many of the automotive companies have got fantastic crusts that just don't have high durability finishes yet.
Thank you, Karl. That's interesting.
Thank you very much.
Thank you. Thank you very much, John.